I'm really excited to be talking to you this morning about some work that I've been doing trying to understand how trait continuity affects the model of song evolution. Of course, learning can be found in pretty much every group of animals, from insects like this honeybee, to fish like this freestone stickleback, amphibians like this salamander, reptiles like this tortoise, and of course in birds like this lyrebird. Learning itself, I think, is a really fascinating phenomenon and produces some really interesting behaviors, but what I'm particularly interested in is understanding how learning interacts with and affects evolution. And the fact that it's so widespread across the animal kingdom, I think, means that it's really important to understand how learning has affected animal evolution. There are lots of behaviors, of course, that are affected by learning, diet, migratory behaviors, cooperative behaviors, predator avoidance, but what I'll be focusing on today is songs and songbirds. And I think there are really kind of two equally plausible arguments for how you might expect for learning to affect evolution. So on the one hand, it's been argued that learning can generate variation more quickly than genetic inheritance, and if that's the case, you might expect learning to actually accelerate speciation or accelerate rates of evolution. On the other hand, birds are using songs to recognize members of their species and to decide with whom to mate. So if they're learning that signal rather than inheriting it, it might allow for interbreeding between populations that are beginning to diverge more easily than if that signal was genetically inherited, in which case we might actually expect learning to impede speciation. So we have these kind of two conflicting intuitions, and I think mathematical model is really a powerful method for kind of addressing that conflict and coming to a more rigorous answer. So there have been many models used to address the issue of song evolution, and the general framework is something like this. So you have males with some song, X, females with some preference, Y, and some preference function that describes the likelihood that they'll mate with any male based on his song. And you can use those these properties to write down the probability of a male with a song X mating with a female with preference Y that's proportional to their frequencies within the population times the preference that a female with that trait has for a male with that song, weighted by the total preferences that the female has for males in the population. And in most models of this type, it's assumed that there's really only a finite number of songs present in the population. So for instance, there might be only 2 songs present, a low song and a high song, for instance. And most models predict that the males who are singing the song preferred by most females will have a higher reproductive success and eventually reach fixation in the population. So here I'm showing, the probability of female preferences in black and the probabilities of male songs in red. And as a few generations go on, as time goes on, those males singing the most preferred song will increase in frequency until eventually they're the only song present in the population. So in other words, in most models, there's been a finite number of discrete songs and preferences, and it's predicted that the most preferred song reaches fixation. There are kind of things that you can add into the model that will help maintain variation. So for instance, you have 2 locations or 2 subpopulations with only limited migration between them, or viability selection against one of the songs, or both. For instance, in this paper that came out in Evolution last year, it's easier to maintain variation in the male song. And so what I'd like to do is argue for a slightly different modification to the model that makes it easier to maintain song diversity. And to do that, we can look at a bird that probably most of you are familiar with, the northern cardinal. And what I'm showing down here is a sonogram of the cardinal song. So on the x-axis is time in seconds, and on the y-axis is the frequency of the song. So you can see he's producing kind of these downward whistles. And there are certainly discrete properties of the song. So he's saying 6 whistles, or 7 if you kind of count this wimpy one. And that's a discrete quality. You can have 5 whistles, or 6 whistles, or 7 whistles. And he has kind of only a finite number of options. But there are also certainly continuous traits here. So his average frequency, or the speed at which he's repeating the whistles, are really best thought of as continuous traits. So I think it's important to consider how both discrete and continuous traits we might expect to evolve under a model like this. So that leads to the questions that I'd like to answer today. So first, I'd like to understand how trait continuity affects the model or affects song diversity. Next, I'll answer how female choosiness affects song diversity, and finally, I'll look at how population size affects song diversity. So to answer these questions, I'll look at a model like the one I just addressed, where the probability of a male with song X and female with preference line mates is proportional to their frequencies in the population times the preference the female has for that male with that song, weighted by the total preferences that the female has for males in the population. And specifically, I'll use this preference function, so just a normal distribution that's maximized at a song that matches the female's preference. And the important parameter here is this sigma squared, which can kind of be thought of as the inverse of choosiness. So that a big sigma squared means you have a very broad preference function, and the female is very permissive in her mating choices, and a small sigma squared means you have a very narrow preference function, and she's very choosy in her mating decisions. So that sets up how males and females within one generation will mate with each other, but we also have to understand how the traits are being propagated from one generation to the next. And I'll be considering two separate cases. So the first, I'll assume that males learn their songs from their fathers, and females imprint on the songs of their fathers and prefer that song. And it turns out to be actually equivalent if both the song and the preference are controlled by the same gene. So in this model, as long as the male song and female preference are being acquired in the same way, the dynamics are really qualitatively the same. The second case I'll consider is one in which the male song is learned from its father, and the female preference is inherited from her mother. And the last thing that I need to describe to kind of get the model going is the initial conditions. And so I'll assume that both the male song and female preference are initially normally distributed. So this is the variance of the male distribution to start with, and the variance of the female distribution to start with. So the song distribution and the preference distribution. So just to kind of summarize the important parameters that I'll be using for the rest of the talk, we have the variance of the preference function, so the width of the female preference function, the variance of the male song distribution, signified with this M, and the variance of the female preference distribution with this F. So what does this look like? Well, in the first case where the male songs and female preferences are acquired in the same way, it looks like the finite model that I just described. So eventually all variance in the male song will disappear. So specifically, if we start off with the distribution of female preferences in black and the distribution of male songs in red, those males singing the songs that are preferred by most females will do better. They'll have higher reproductive success, and they'll increase in frequency. And over time, they'll continue to increase until they're the only ones present in the population. I think something's really kind of more interesting going on in the second case, and in this case, you can actually show, remind you, the second case is one in which the males are learning their songs from their fathers, and the females are learning or inheriting their songs from their mothers. You can show analytically that in the limit of infinite generations, as time goes on, the variance of the male song distribution will be exactly equal to the variance of the female preference distribution discounted by the weight of the preference distribution, a preference function rather. And if this quantity happens to be negative, then the variance of the male song will actually be 0. So what does this one look like? So what's going on here is, so again, I've shown the female preference function distribution in black, and the male song distribution in red. And in this case, it's actually the males in the tail of the distribution who are doing better because they get to mate with these females out in the tail who are really desperate for males. So in the right panel, I'm showing the growth rate of the various songs, which is just the ratio of the males singing the song in the next generation to the number of males singing that song in the current generation. And if they line this one line, that means that they're not changing over time. And you can see that males kind of away from average are actually doing better because they're being preferred by these tail females. So after a few generations, the distribution of male songs is actually becoming wider because these males in the tail are getting to mate with desperate females. And as time goes on, eventually we reach equilibrium where all males are not growing anymore. And there's kind of a trade-off between the advantages to being in the tail of the distribution, and you get to mate with desperate females who are out in the tail, and the advantages of being in the middle, and you get to mate with all of the very frequent females in the middle of the distribution. So to kind of wrap that up, the effect of trait continuity, so the effect of considering a continuous trait in this model is that song variance can be maintained as long as males acquire songs and females acquire preferences from different parents. To address the effect of choosiness in this model, I'll come back to this quantity that I introduced earlier. So as I said before, the equilibrium limit of the variance in the male song distribution is equal to the variance of the female preference distribution discounted by the sigma squared factor. So you might expect that If females are really choosy, that would introduce really, really strong selection, and that would be the situation in which you would only have one song present in the population. And I'm actually finding the opposite. So the smaller this sigma squared is, the more choosy the females are, and the larger the variance of the male song distribution is. So choosiness actually increases the variance at equilibrium, in this case where males and females are learning or acquiring their songhood preferences from different parents. The last kind of tweak to the model that I'd like to talk about is one in which I consider a finite population. So far I've been considering these very nice normal distributions where you can have any probability of song present. But if you have a small population, say 1,000 members, saying that there's a probability of 1 in a million of having a song doesn't really make much sense. So if I simulate this model, but assume that there's some threshold such that if the frequency of males singing that song drops below the threshold, I just kind of remove them from the population, you get something a little bit more interesting. So in the top here, I'm showing the equilibrium of the model as I just described it. Sorry. And in the lower panel, I'm showing the equilibrium of the model where I've removed males from the population once the probability of males singing that song dropped below a certain threshold. And you get this really interesting kind of wave function. So the probability distribution gets concentrated at a finite number of peaks. I don't think I have time to talk about kind of the mechanisms for why that comes to be, but I can talk about it later if you're interested in it. And I think this is really interesting that it can tell us something about the type of variation that we might expect to see in natural populations. So to summarize, with continuous traits, I've found that variance in song can be maintained if song and preference are acquired from different parents. I also found that increasing female choosiness actually increases the variance present in male songs. And finally, that discrete kind of popular songs can appear even though both song and preference are continuous traits. So with that, I'd like to thank my funding agencies, my home institutions, and thank you for listening.